Thin film interference is the same idea that two stones dropped in a pond create overlapping ripples. Light that hits a thin layer, think of a soap bubble or a lake water skin, is partially reflected from the top surface and partially transmitted, then reflected again from the bottom surface. The two reflected rays travel slightly different distances. This extra distance is called the optical path difference, OPD. OPD equals 2nt cos theta, where n is the film's refractive index, t its physical thickness, and theta the angle inside the film. When a wave reflects from a medium of higher refractive index, it gains a half wavelength pi radian phase jump. Reflecting from a lower index does not. By adding the phase change from the path length and the possible pi shift, we can use simple superposition, adding the two electric field vectors, to see whether the two reflected beams reinforce, bright, or cancel dark. An everyday analogy is two people shouting in a hallway. If one steps back a half step before shouting, their voices may cancel at some points. For light hitting a film straight on, normal incidence theta equals 0. The optical path difference reduces to 2nt. Constructive interference, bright reflected light, occurs when this extra travel equals an integer multiple of the wavelength lambda in the surrounding medium. 2nt equals m lambda, with m equals 0, 1, 2, and so on. Destructive interference, dark reflected light, happens when the optical path difference is a half integer multiple. 2nt equals open parenthesis m plus 1/2 close parenthesis lambda. Example, a film with n equals 1.5 and lambda equals 600 nanometers. To get a dark fringe, first order, m equals 0, we need 2 times 1.5 times t equals 1/2 times 600 nanometers, which gives t equals 100 nanometers. For a bright fringe of order m equals 1, 2 times 1.5 times t equals 1 times 600 nanometers, giving t equals 200 nanometers. The factor of 1/2 in the destructive condition comes from the extra pi phase shift that occurs when the top surface reflects from a higher index medium, air to film, while the bottom surface reflects from a lower index medium, film to substrate. When light strikes a film at an angle, the simple 2nt formula must be modified because the light travels a longer slanted path inside the film. Snell's law n0 sin theta 0 equals n sin theta gives the internal angle theta. The optical path difference becomes 2nt cosine theta, which reduces to the normal incidence case when theta equals 0. Moreover, the reflection coefficients differ for s, perpendicular, and p, parallel polarizations, leading to slightly different phase shifts. The generalized constructive condition is 2nt cosine theta equals m lambda, while the destructive condition is 2nt cosine theta equals m plus 1/2 lambda. In practice, for a thin film anti-reflective coating on a camera lens, designers calculate the optimal thickness for the most common viewing angle approximately 0 to 30 degrees, and check both polarizations to ensure the coating works for unpolarized light. An easy analogy: walking across a shallow stream at an angle makes your path longer than walking straight across. The same extra distance changes the timing of the waves you create. The reflected intensity from a thin film is not just bright or dark, it varies smoothly with wavelength. By adding the complex electric field amplitudes, we obtain the Airy formula. R equals open parenthesis R sub 12 plus R sub 23 plus 2 times the square root of R sub 12 times R sub 23 times cosine delta close parenthesis, divided by open parenthesis 1 plus R sub 12 times R sub 23 plus 2 times the square root of R sub 12 times R sub 23 times cosine delta close parenthesis. Where R sub 12 and R sub 23 are the Fresnel reflectances at the two interfaces, and delta equals 4 pi nt cosine theta divided by lambda, the round-trip phase. The finesse f equals 4r divided by open parenthesis 1 minus r close parenthesis squared for identical interfaces, measures how sharp the peaks are. Higher f means narrow, high-contrast fringes. The contrast, also called visibility V, equals open parenthesis I max minus I min close parenthesis, divided by open parenthesis I max plus I min close parenthesis. It can be expressed as V equals 2 times the square root of R sub 12 times R sub 23 divided by R sub 12 plus R sub 23 when absorption is negligible. Real-world example: Fabry-Perot etalons used in laser cavities rely on high finesse to select a single wavelength, analogous to how a set of parallel mirrors, a thin film, acts like a wavelength filter. When more than one layer is stacked, for example anti-reflection coating plus protective layer, the simple two-interface formulas no longer work. The transfer matrix method treats each layer as a 2x2 matrix that relates the forward and backward electric field amplitudes at its boundaries. M sub j equals a matrix with cosine delta j in the top left, I over q sub j times sine delta j in the top right, iq sub j times sine delta j in the bottom left, and cosine delta j in the bottom right. Where delta j equals 2 pi times n sub j times d sub j times cosine theta j divided by lambda, and q sub j equals n sub j over n0 times cosine theta j for s polarization, or q sub j equals n0 over n sub j times cosine theta j for p polarization. For a stack of capital N layers, the overall matrix M equals M sub 1 times M sub 2, and so on up to M sub n. The reflectance is then R equals the absolute value squared of the fraction with numerator M sub 11 plus M sub 12, Q sub S minus M sub 21 divided by Q sub S minus M sub 22, over denominator M sub 11 plus M sub 12, Q sub S plus M sub 21 divided by Q sub S plus M sub 22. With Q sub S representing the substrate side. This method lets engineers quickly compute the spectral response of complex coatings. For example, a 7-layer broadband anti-reflection coating on a solar cell, by simply multiplying matrices on a computer. Anti-reflection AR coatings aim to cancel the reflected wave. The classic design uses a single quarter wave layer. Thickness T equals lambda 0 divided by 4n, where lambda 0 is the wavelength at which we want minimum reflection. The refractive index is chosen as the geometric mean of air, n approximately 1, and the substrate n sub s. N equals square root of n sub s. For a glass lens, n sub s approximately 1.5, the optimal AR layer has n approximately square root of 1.5 approximately 1.22. Magnesium fluoride 2. The quarter wave thickness makes the two reflected waves 180 degrees out of phase, producing destructive interference. For high reflectivity HR mirrors, for example laser mirrors, we instead use many alternating high index, n sub h, and low index, n sub l, layers each of quarter wave thickness. The stack creates a large impedance mismatch, reflecting greater than 99.9% of light. Bandwidth is controlled by the number of pairs. More pairs give higher reflectance but narrower bandwidth. Designers trade off between thickness, mechanical stress, manufacturing cost, and spectral width, much like choosing how many layers of paint to apply to a wall for both durability and color depth. Use quarter wave condition. T equals lambda divided by 4n equals 550 nanometers divided by 4 times 1.38, approximately 99.6 nanometers. Compute Fresnel reflectance at air magnesium fluoride. R1 equals 1 minus 1.38 divided by 1 plus 1.38, all squared approximately 0.028. At magnesium fluoride silicon interface, R2 equals 1.38 minus 3.5 divided by 1.38 plus 3.5, all squared approximately 0.138. Net reflectance using the two-interface formula. R approximately R1 plus R2 minus 2 times the square root of R1 times R2 times cosine delta, where delta equals 4 pi nt divided by lambda equals pi quarter wave, so cosine delta equals -1. Plug numbers. R approximately 0.028 plus 0.138 plus 2 times the square root of 0.028 times 0.138 equals 0.166 plus 2 times 0.062 equals 0.29, approximately 29%. This is the reflectance without the phase condition. With delta equals pi, the cosine term becomes -1, giving destructive interference. R equals R1 plus R2 minus 2 times the square root of R1 times R2 equals 0.166 minus 0.124 equals 0.042, approximately 4%. Thus the coating reduces reflection from about 30% for bare silicon to about 4%. Another example. Design a high reflectivity mirror for lambda 1064 nanometers using 4 pairs of titanium dioxide with high index 2.4 and silicon dioxide with low index 1.45. Each layer thickness equals lambda divided by 4n compute T, high equals 1064 divided by 4 times 2.4, approximately 111 nanometers. T low equals 1064 divided by 4 times 1.45, approximately 184 nanometers. Using the transfer matrix method or the approximate reflectance formula, our approximately open bracket n high divided by n low close bracket to the power of 2n minus 1 divided by open bracket n high divided by n low close bracket to the power of 2n plus 1 squared, with n equals 4, gives R approximately 99.5%. These steps illustrate how to turn a textbook formula into a practical design. Derive the condition for destructive interference at normal incidence. Write optical path difference equals 2nt, add pi phase shift for high to low index reflection, set total phase equals open parenthesis 2m plus 1 close parenthesis pi. Therefore 2nt equals open parenthesis m plus 1 half close parenthesis lambda. Calculate the thickness of a magnesium fluoride anti-reflection coating for lambda equals 650 nanometers on glass, with n equals 1.5. Thickness equals lambda divided by 4n equals 650, divided by open parenthesis 4 times 1.38 close parenthesis approximately 118 nanometers. Given a 2-layer stack with n sub 1 equals 2.0, d sub 1 equals 1/4 lambda, n sub 2 equals 1.5, d sub 2 equals 1/4 lambda, compute the reflectance at lambda using the transfer matrix. Build matrix 1, matrix 2, multiply them. Then use reflectance equals absolute value of open parenthesis matrix 111 plus matrix 112 q sub s minus matrix 211 divided by q sub s minus matrix 212 close parenthesis divided by open parenthesis matrix 111 plus matrix 112 q sub s plus matrix 211 divided by q sub s plus matrix 212 close parenthesis all squared. Explain why a soap bubble shows colorful fringes. Varying thickness T leads to varying optical path difference 2nt, causing constructive and destructive conditions for different lambda across the visible spectrum. Design a broadband anti-reflection coating from 300 to 800 nanometers using 3 layers. List material indices and thicknesses. Choose alternating refractive indices approximately 1.2, 1.7, 2.2, each quarter wave at the center wavelength 550 nanometers, then discuss how the multi-layer widens the low reflectance band. Compute finesse for a Fabry-Perot etalon with mirror reflectance R equals 0.9. Finesse equals 4R divided by open parenthesis 1 minus R close parenthesis squared equals 4 times 0.9 divided by 0.1 squared equals 360.